Hello, everyone. Welcome to Theo-MathProblemSolver. From the basic definitions to real-world applications, this episode will provide a comprehensive overview of the relationship between, velocity and acceleration, and their role in describing the motion of objects. Please join me even as we explore the fascinating world of motion and unlock the secret of velocity and acceleration. Please don't forget to like, share, and subscribe for more educational content. Quick, recap on the notion or the concept of rate of change. So if x changes from, so suppose x changes from x1 to x2, then we claim that the change in x will just be what? X2 minus x1, okay? Because x is changing from x1 to x2. Then its change now becomes what? X2 minus x1. Then what then becomes the corresponding change in y? So if that's the case, the corresponding change in y becomes what? F of x2 minus f of x1. Suppose that y is equal to f of x. Is that okay? Suppose y equal to f of x, and x is changing from x1 to x2. Then the change in x would just be what? X2 minus x1, and its corresponding change in y would just be f of x2 minus f of x1. Is that okay? Then we went further to say that the difference quotient would then be what? What then becomes the difference quotient? The difference quotient, as the name implies, quotient, which becomes just going to be the ratio of the change in y with respect to the change in x, right? So it's just going to be the ratio of change in y with respect to change in x. In which case we're going to have f of x1 minus f of x2, or on x2 minus x1, right? But we said that your x2 should never be same as x1. This is very, very important. And we also made mention of the fact that this is also known as what? The average rate of change of y with respect to x over the interval x1 to x2. Okay, very good. Very good. And we also said that this can also be interpreted as the what? As a slope of the secant line, let's say from one point to the other. Okay, that's very, very important. And we also went further to claim that if this change in x approaches zero, if the change in x is very, very, very small, then we claim that then we have the first word derivative. Okay, so we claim that if the change in x approaches zero, in other words, it's very, 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 very small as far as this ratio is concerned, then we claim that we're going to have what? Then we're going to have what? Our change in y with respect to change in x. And such notation, which is change in y with change in x, notation was propounded by who? The mathematician Leibniz. Okay, he came out with this notation, which is dy dx. I want us to take note. Okay, this is very, very important. So today we are looking at a very important concept that we know. It is known as velocity and that of acceleration. So let's take note of that. So velocity and acceleration. Okay. So let's take it. Now in physics, I know that in physics, this is a very important concept that, it's important that you do not want to miss. You have to understand the basis of, when we talk about velocity, what does it mean? We talk of acceleration. Okay, so we're going to employ all of those strategies, all those techniques for us to tackle issues, especially in relation to mathematics. Okay, so suppose S of t, so usually we use S of t. Suppose S of t is the position function. Okay, suppose that this is the position function, okay, of a particle that is moving in a straight line. Then we claim that the change in such a position function over time with respect to the change in time represent the average velocity over the time, okay, over the time period, which is change in t, okay. So in that case, we're going to have this as our average velocity over time, okay. In which case, we're going to have our velocity to be equal to what? Change in x over change in what? In t. That is, if we apply limit on this, if we apply limit on this as t approaches zero, then this can also be written as this, okay, in a very simple way. So anytime I ask you to find the velocity, so this represents our velocity. So anytime I ask you to find the velocity of an object, it's just going to be the position function, the change in the position function with respect to time, okay? That is very, very important. So I would want us to take note. Or what we call the rate of change of displacement with respect to time. So let's take note. Now, what about the acceleration? If the velocity is this, then what then becomes the acceleration? What then becomes the acceleration? If the velocity is defined this way, what then becomes the acceleration? So our acceleration will just be what? It's just going to be the derivative of the velocity, okay? Which can also be written as what? Which is the same as what? S prime of t, okay? So I would want us to take note that this is the same as that. So let's take note of that. Now let's look at some few examples and see how best we be able to understand this concept. Now, if the position function of a particle is given by the equation, so if the position of a particle is given by the equation t to the power 3 minus 6t squared plus 9t. Now the first question is where t is measured in seconds. So please take note that t is measured in seconds and s is measured in meters. So let's take note. Now the first question is that find the velocity at time t, okay? So we should find the velocity as time t. And then the B part is that we should, so let's solve it one after the other. What then becomes our velocity? So we claim that the velocity is just going to be the what? It's just going to be changing the position of the particle with respect to time, okay? So in that case, our velocity will just be what? S prime of t. So in which case, you're going to differentiate this. So by differentiating this, what do we get? We're going to have 3t to the power 2 minus what? 12t plus what? Plus 9. Good. So that is going to be our velocity. If you have any questions, please put it in the comment section, then we'll attend to you guys. At this moment, I want you to take time to, if you have not subscribed, please subscribe, share the link to your colleagues, and then also let them also share it with their other mates as well. So the B part, if I ask you to find then what is the velocity after 2 seconds? Now, if I ask you this question, that what is the velocity after 2 seconds? If I ask you this question, what will you do? What's the velocity after 2 seconds? So it just means that wherever I see t, I should just replace it by 2. And that will be the result. It just means that wherever I see t, I should just replace it by 2. Okay, and that will be the result. And that should give us which result? And that should give us what? That should give us what? That will be minus 3 miles per second. Okay, good. So let's take note of that. Now, if I ask you this question that what is a particle at rest? Is a particle at rest? So if I ask you this question that when is a particle at rest? When then what will be our response? So you could pause the video and try and see whether you'll be able to solve this one. When is a particle at rest? So the particle is at rest when the velocity is 0, right? So we claim that the particle is at rest when the velocity is 0. So in which case, already we know our velocity, right? We've been able to calculate our velocity. So what it just implies that my v of t should be equal to 0. But already we know our velocity to be what? 3t minus what? 12t plus 9. So what we do is we just set it to 0. And by how do we solve this? So by solving this, you just have to, the easiest way is to maybe pull out the 3. So we can pull out the 3. Okay, we can factor out the 3. And that gives us what? Over here. So we get 4t plus 9 equal to 0. So in which case, you're going to have what? T squared minus 4t plus 3 equal to 0. That's if you divide both sides by 3, right? You have something like this. And when you further simplify, you should have what? By factorizing, you should have t minus 1, t what? Minus 3 equal to 0. In which case, t is equal to 1, t is equal to 3. Okay. So let's take note. I want us to take note of this one, please. Let's take note. What about if I ask you to find the acceleration? If I ask you to find the acceleration of the particle, if I ask you to find the acceleration of the particle, then it's just going to be what? The derivative of the velocity, right? So acceleration, we said that acceleration is just going to be what? It's just going to be what? The derivative of the velocity. Okay, so let us take note. Now, but what is our velocity? Our velocity was given as what? So let's write it down here. We know that our velocity is what? 3t squared minus 12t plus 9. Now, what is the acceleration? So the acceleration, we said that we just have to differentiate the velocity, and that gives us what? 6 minus 12, right? So that is going to be our acceleration. I hope we all get this question. If you have any further questions, please do let me know, okay, so that we can tackle it. All right. So this is our second problem as far as velocity and acceleration is concerned. Now, I would want us to look at this question with a different kind of mindset and try to see whether we can recall some of the definitions of some of the definitions as far as their derivative is concerned. All right, so now the question is that the position of a particle is given by such function, then where we claim that S is in miles and T is in hours. Now the question is, how do we find the distance, the velocity, and the acceleration when T is equal to 4 hours? It's a very nice question. So I think we would want to, take our time to really understand it so that we can appreciate it as well. Now, how do you find a distance? The position the particle is given by this. How do you find a distance when T is 4? Anyone with an idea? So it means that the distance will just be what? So the distance will just be where it means that wherever we see T in the given function, we just replace it by 4, right? So S of 4 should be equal to 10 multiplying 4 to the power 9 plus root of 4 plus 2, 4 to minus 2. And that should give you the result, right? And that would give you the result. All right. So when you use a calculator, that should give you the result. So what about the velocity? What did you say about the velocity? How do you find the velocity? So the velocity, we said that what is just going to be the first derivative of the position. It's just going to the position of the particle, right? And what would that be? That's going to, this has to do with the power rule. So we drop the 9, multiply the 9 by 10, that gives us what? 90, then we decrease the power by 1. So in that case, we're going to have what? 90 t to the power 8 plus. Now, the easiest way to look at this is try to write root of t as what? T to the power half, right? So t to the power half. So what happens? We drop the half, then we decrease the power of the t by 1. That gives us what? Minus. Then the same applies to the other one. So that gives us minus 4 t to the power minus 3. It's very, very important. Then when t is 4, what do we get when t is 4? Just means that wherever I see t, I should just replace it by 4. Okay, good. All right. So you can put the result in the comment section, then I'll cross-check it and see. Okay, good. Now, what about the acceleration? What then becomes the result for the acceleration? We claim that acceleration, which is denoted of a of t, is just going to be what? The derivative of the velocity. Okay, and then what then becomes the derivative of the velocity? This is our velocity, right? This is what we had as our velocity. What then becomes its derivative? So you can pause the video and see whether you'll be able to do it by yourself. And let's see. What did we get? So when we differentiate the velocity, that should give us what? 20t to the power 7, right? And that should give us what? Minus 3 on 2. And that gives us what? T to the power minus 4. Now, when we evaluate this at t is equal to 4, what it just means is that wherever we see t, you just replace it by 4, and that should give us the result, right? So you can also put your result in the comment section, then I'll cross-check that and I'll attend to you. All right, so let's go to the final problem of the day. Now, the question is that a pebble is dropped from a hot air balloon. Now, the question now, how fast, it says that how far has it fallen and how fast is falling. And we also want to find out its acceleration after 3.5 seconds. So note that the position function is giving us 16 times t to the power 2, or 16 t to the power 2, where we also say that t is in seconds and s is in feet. Now the question is, how do we find how far it has fallen? How do we do that given the position function? So which is the distance, right? It says how far it has fallen, which is the distance. The distance will just be equal to what? Will just be equal to what? So in which case we're going to use a position function and evaluate that when the t is 3.5 seconds, right? So in which case we're going to have 3.5 seconds and plug it into the system, into the position function. And that should give us what? That should give us 196 feet. Remember, the position function is measured in feet. So I want us to take note. And then the next question is that how fast is falling? How fast it is falling? So I want us to take note. What does it mean? How fast it is falling? So how fast it is falling? So we're looking at the rate at which it is falling with respect to time, which has to do with what? Velocity, okay? So how fast it falls, in which case we're talking about the rate of change, and that has to do with what? With velocity. So our velocity will just be what? Our velocity, we said that what? It's just going to be the first derivative of the position function. And then the position function is what? 16. So 16 by 2, and that gives us what? 32t. Then we go further to evaluate it at 4. Okay. So we are going to evaluate the velocity at t equal to 4. at t equal 3.5 seconds. So let's take note. So that is going to give us 112 feet per second. So I want us to take note. What about the acceleration? What then becomes the acceleration? Per definition, we said that the acceleration is equal to what? The first derivative of the velocity. And when you differentiate the velocity, what do we get? That will give us 32. And when we evaluate the velocity at 3.5, we should be able to get the same thing, because the result is constant. So in that case, you could have feet or seconds squared. So let's take note. The second squared. So I want us to take note. So velocity is measured in this case, we'll be measuring in feet per second squared. So I want us to take note. Once again, if you have not subscribed to my channel, please do so. Subscribe, like, comment, and then share the content to your colleagues, to your loved ones, and let's keep this good news. Thank you so much for your time.